I have two quick announcements. One is that there will be a social program followed by dinner this evening. So the social program will be here at the same hall at 6:15. And this will kick off by a talk by Sanjeev Dhurandhar on the early days of gravitational wave research in India, and followed by some of our colleagues will say something about their experiences working with Bala and so on. And will be followed by a dinner which will start at 7:30. So the social program is here at 6:15. So all of you are invited for this. And secondly, 6:15, soon after the second session. Secondly, after this particular session, during the coffee break, we would like to take a group photo of, and please assemble just in the small lawn towards the left when you exit from here. So soon after this program, before the coffee break, we will have a group photo.
Okay, so let's get started with the first session of this afternoon. So this is the cosmology session. Cosmology using gravitational waves. We have 4 presentations, one overview starting with Archisman, 25 minutes, and then 3 15-minute presentations. As you see, there's a little arrow with Z. We tried to sort of order this in increasing redshift cosmologically all the way until we're talking about inflationary gravitational waves at the end. But we're starting with Archisman, who's going to focus mostly on ground-based cosmology with compact binary coalescences. I should add as well, please ask questions of the speakers during this talk, unless they say otherwise, which would be strange. But we're going to hold off on any questions at the end of each presentation for a discussion session at the end, and I'm going to get all of the speakers to sit in the panel, despite whether or not they want to, I don't know, but and we'll try and have a panel discussion at the very end.
Numbered 1.
So I'll stop talking. Oh, and I want to say it's a great honor as well to be invited to chair this session, Bala, at this event. Okay.
Thanks, Chris. It's an honor to be back, honor to be speaking here, and a pleasure to be back talking about some work, aspects of which I'd started 6 years back here in ICTS. And before I move on, since this is a event in honor of Bala, it's worth taking 2 minutes mentioning some of the things about the time when I first moved into the new field and got to know Bala. Of course, the first thing that you get to hear about Bala is that you should be scared of Bala. But very soon you get to know that you need to be scared of Bala only if you're trying to take a shortcut, if you're trying to slack off. And this general fear of Bala, of us meeting 2 times every year for our Indigo MOUs, actually meeting deadlines, sitting together, or working with other colleagues, junior postdocs, graduate students, that created a very productive environment among us and has probably pushed many of us towards our current activities. Thanks, Bala. So I'll follow the same format of the rest of this panel, and I'll slowly progress from lower to higher redshifts. And this overview will be from the compact binary perspective. A very important aspect of gravitational wave cosmology is that of the background, both the primordial and the otherwise stochastic background, and these aspects are going to be covered by Sriram. So the main idea here, which most of us are familiar with, is compact binaries are standard sirens. For compact binaries, we can independently measure the phase as well as the amplitude because these are coherent sources. From the phase evolution, we can already measure the chirp mass. We can plug this back into the amplitude and directly measure the distance independent of all other measurements, and we can measure the distance in particular independent of the cosmic distance ladder. The distance is something that we need to measure cosmological parameters like the Hubble constant, like the matter fraction, dark energy fraction, but along with the distance, we also need the redshift. So the question is, where does the redshift come from? For compact binaries, the gravitational wave redshift is largely degenerate with the total mass. I'm going to come back to this on my last slide once again. So in most of my talk, we are going to assume that there is something electromagnetic which provides us a redshift. It could be a transient electromagnetic counterpart. It could be a host galaxy. It could be a set of possible host galaxies. With a transient electromagnetic counterpart to GW170817, the first binary neutron star we discovered, we could get the first standard siren measurement of the Hubble constant. As you can see, here's this great measurement that we have, the first measurement. Along with that in the background, we see the other state-of-the-art estimates back then, which are from Planck and Schultz, the early universe CMB, and the local supernova experiments respectively, which do not agree with each other. There's a discrepancy. The current measurement agrees with both the state-of-the-art measurements. I do not want to highlight what the actual value of the peak is because the measurement is so wide. I just want to point out that the error currently with this one standard siren is about 14%. I will very briefly mention a few more things about the discrepancy. This is going to be covered in detail by Souradeep in the next talk. The discrepancy has been the early universe measurements, and the measurement with supernova, local supernova have been moving apart. And about a month back, the supernova calibrated with these tip of the red giant branch, they have, in the intermediate regime, have come to lie between these two measurements. So this discrepancy could be some systematic effect. This discrepancy could be of cosmological origin. We are sure going to hear more about this soon. But the Planck measurement, for example, is at 0.7%, and the Schultz is at about 2%. So this is the kind of accuracy that we should also be aiming for with standard sirens, about % accuracy. How can we get to a % accuracy? Of course, we can combine information from multiple detections. And if we have very similar detections, then the precision should scale as 1 over square root of n, where n is the number of events we detect. We are now at 14%. We need to go to 1%. How many detections do we need? 14 square, which is roughly about 200 detections that we see from this set of simulations. Of course, we are better with more detections, but something that has come up many, many times over the last few years is that we need to be very, very careful about handling systematic effects, including gravitational wave selection effects. In particular, we need to take into account these selection effects by calculating the detection efficiency, which is what you would expect, on top of the prior, just because you are not detecting all the events, but preferentially louder events, the ones that are closer by or the ones that are face on as opposed to edge on. And one needs to divide out by this detection efficiency or this selection function. Another important thing to highlight is what I showed in my first plot is not the best thing that I could show you. What I should have shown you is this plot over here, which shows the Hubble constant and the inclination, which shows the Hubble constant on one axis and the inclination on the other axis. Because the gravitational wave distance measurement is strongly correlated with the inclination, so is the Hubble constant. This is what we have actually measured. The first plot that I showed you has been marginalized over all possible inclinations. If there is some other experiment that can measure the inclination for us, then we should be able to get a better measurement of the Hubble constant. Yes? This is assuming the standard prior which you expect on the inclination, which is this prior on the sphere.
It's not from astrophysics.
No, this is just the expected prior, which is uniform in cosine iota, uniform in cosine inclination.
I guess but changing this prior doesn't change your result by what?
It shouldn't change by much, but the thing is, this result, for example, has been depends on what your prior is, right? I mean, here what you have done is you have essentially marginalized not over the uniform prior, but over a narrower prior, and that has improved the measurement. So I take back my first statement. The prior really does matter here. Okay.
What is the other experiment that can measure the inclination that you're talking about?
Yeah, I haven't come to that.
Oh, okay.
Sorry. So the VLP, they observed a jet long after the merger, and from the jet and their associated jet models, I'm not sure if Kenta is here, from the jet and the associated jet models, they could measure the inclination, they could get an estimate of the inclination, and that narrowed the measurement of the Hubble constant by this much, as you see in the figure. So if you trust these jet models, which I believe are not perfect, and the measurement, then you do get a much better measurement of the Hubble constant than what we had from the raw gravitational wave data and NGC 4993. Yes. I'll move on since I think I spent more time on this than I wanted to. So the question is, how many binary neutron stars are you going to observe which have counterparts? In O3, we already have one or a few binary neutron stars that we have seen without electromagnetic counterparts. So there could be binary neutron stars without electromagnetic counterparts. There could be sources like binary black holes, which are expected without any counterparts. So it would be good to work with sources for which you do not see counterparts or for which you do not expect counterparts. And there comes in the galaxy catalog method due to Bernard Schultz. The idea was, of course, in Schultz. It was implemented. It was explored in the context of LISA by MacLeod and Hogan. And there are some further, more recent references. But more importantly, how does this method work? This is best illustrated in this set of animations, which go as follows. If we have a distance estimate and a unique redshift value like we had for GW 170817, then we get a nice estimate of the Hubble constant. But let's say we do not have a unique redshift. Let's say we have a few possible galaxies. Let's say we have 5 possible host galaxies. So instead of one single peak over here, we see 5 different peaks. And each of these 5 peaks, they should peak at a different value of h0. And some of them are close by. These peaks should fuse together. And here you see the resulting h0 distribution. You see 3 peaks of different width. You do not know which is the correct peak. You do not know what's the correct h0. If you have an entirely different observation in a different part of the sky, you have an entirely different distance estimate. So entirely different set of host galaxies, you get a similar multimodal h0 estimate, which does not carry any useful information. However, if you put together many such observations, if you put together many such independent observations, then what's going to happen on an average is that the peak at the correct location is going to get enhanced, while the peak at the incorrect location are going to get suppressed because they're at random values, while the peak at the correct location is at the correct value. And you're going to get a nice estimate on the Hubble constant. Here also, selection effects become important. Since we are working with galaxy catalogs, we need to worry not only about the gravitational wave selection effects, which I already mentioned, we also need to worry about the electromagnetic selection effects, which is essentially the fact that the galaxy catalogs are not complete because the optical telescope has a limited sensitivity. So we have devised a method which takes into account, in addition to the in-catalog component, there's an out-of-catalog term, and this term essentially takes into account the fact that there are galaxies beyond the catalog, galaxies of which the exact redshift we do not know. And we have come up with an integrated method of taking into account both these effects. We have applied these methods to some simulations, and I will show you the results of the simulations shortly. Just before that, let me highlight that these simulations have been performed at BNS-like distances. So these are simulations for essentially binary neutron stars without counterparts. They have been performed with galaxy catalogues that are about 35 times sparse in one case and about 3 times dense in the other case compared to a real galaxy catalog. There are order 10 to 100, maybe a few times more galaxies per event. And various sophistications such as redshift uncertainties and galaxy clustering have been ignored. With these assumptions and this set of simulations, this is the result that we get for both the counterpart and galaxy catalogues of varying completeness. A galaxy catalog that's 100% complete, a galaxy catalog that's 75% complete in green, 50% complete in orange, and 25% complete in blue. And as you can see, all these results, after the number of events become large enough, they start scaling as 1 over square root of n. It takes some time, especially for the sparser catalogs, before this scaling sets in. And we also see that we are not much worse off without an exact counterpart, provided the galaxy catalogs are reasonably complete. Here we see only a factor of 2. It might be a factor of 3 or 4 in reality, but it's essentially a factor of few at these distances, which you lose out because you do not see the exact counterpart. You do not identify the exact host galaxy.
But the inclination priors are the same.
Yes, no, the inclination scenarios are the same, and here we assume that we essentially do not know the inclination, so it's the uniform inclination prior. Yes.
Because I think perhaps I didn't understand what you are plotting. So in the case of the counterparts, you assume that's a binary neutron star?
Yes.
And in the other cases, you are allowing, so you are not using a counterpart. When you talk about 20% per complete, you are using the method, the statistical method.
Yes, and we are using a simulated galaxy catalog, which is about 100 times sparse compared to a real catalog.
But is there the information on how well you can localize in this plot?
Yes.
Is that included? That you because depending, I thought that one problem is how many galaxies there are.
Yes. So that is essentially the main problem. So here we have used localizations from the first 2 years scenario. So it's a 3 detector network. However, the galaxy catalogs themselves are sparse. The galaxy catalogs have about 100 times fewer galaxies than they should have, where in reality they should have about 10,000 galaxies. Here they have only about 100. So the galaxy catalogs are sparse.
Is realistic what you are showing here?
The thing is, it is, okay. Now I'm going to make some statements that are based on my intuition, not based on exact simulations which we have performed. With about 100 galaxies, 100 possible host galaxies as opposed to a unique counterpart, we are worse off by a factor of 3 here. It essentially works like you need about 10 times more events to come to the same precision, and because the precision falls over as 1 over square root of n, you need about, it is about a square root of 3. Now, if you have 100 times more galaxies, you would need 100 times more the number of events to come to the same precision, and for the same number of events, you would not be about 3 times worse, but you would be 10 times worse. Yes, but, okay. But that does not, here we have only 200 events. 2,000 events is probably not very unrealistic. I'm going to come to things that can improve this, that can make this worse. How much time do I have? 7 minutes. Yeah.
But you're still limited to realize a volume for binary universe. 2000 units.
No. Discussion period. Okay, so something that can improve this estimate is weighting of galaxies by their luminosities. We can expect that the more luminous galaxies are also the more preferable hosts, so we can weight galaxies we can weight the probability of galaxies in proportion to their luminosities. For example, the B-band luminosity may be a proxy for the star formation rate, the K-band luminosity may be a proxy for the total mass. So essentially, so if we assume that more luminous galaxies are more likely hosts, that means that we are probably also have more of the correct hosts in the catalog than the dimmer galaxies, which are anyway probably not hosting most of the events. So if we fold in luminosity weighting, we see that with the H0 estimate, this is again with the full set of 250 events, the H0 estimate improves by about this factor. And it has also been explored independently that if we want to put in galaxy clustering, then galaxy clustering improves the estimate by about a factor of 2.5. These are of course things that improve the estimate. We are not taking into account things like redshift uncertainties, which are going to worsen the estimate. I'll very briefly flash a few slides on the results. This is the first application of the H0 statistical method for GW170817, assuming that there was no counterpart. Then we had an estimate from GW170814 with the DES catalog, with the DES survey, which surveyed the GW170814 sky localization very well. And this is the kind of estimate we obtained given certain caveats that we put certain redshift cuts in obtaining this estimate. And more recently, as of yesterday, we have the result from all O1 and O2 detections, and this is the curve in blue is the current best estimate on H0, which we have from GW observations. Here we have tried to use all the events, not necessarily all the events. We had 10 black holes. We used only 5 of them, which are shown as solid lines over here, because for the 5 of them, we believe that these galaxy catalogs are complete enough that no systematic effects are introduced by taking into account the incompleteness. More details are, of course, in the paper, and I unfortunately do not have a lot of time to spend on this. I'm happy to bring this further to discussion. I'll move on, and these are the few things that are going to be important very soon: photometric measurements of redshifts, luminosity weighting, and population properties of galaxies which enter the selection function are also very important, which we need to understand better. Of course, eventually we are going to hit waveform systematic effects and detector calibration uncertainties. However, we are still far from there. This concludes my discussion on ground-based detectors or advanced ground-based detectors. For other cosmological parameters, at least from the simulations that have been performed, it seems that advanced ground-based detectors might not be sufficient. One would need to go to either 3G or space-based detectors. And some of these experiments might also simultaneously probe modified gravity along with cosmology. A very quick slide about LISA, which is not my own slide, but a slide from Nicola Tamanini. And LISA is going to have give us a number of different sources like stellar mass binary black holes, extreme mass ratio in spirals, and massive or supermassive black holes, which are also expected with counterparts. So LISA opens a whole new window to gravitational wave cosmology. These are some results on LISA projections, again from Nicola Tamanini. Something else that would be brought up in the discussion, would probably be brought up again by Suhud and in the discussion session, is how to use correlations, both how to use correlations between the gravitational wave observations and electromagnetic observations in order to improve the estimates, in order to improve the H0 estimates either for the current generation or more likely for future generations. And there's also some ongoing work in ICTS in this context. I mentioned that we need an EM counterpart to do gravitational wave cosmology, but there can be scenarios where we do not need any EM counterpart, where the information can essentially all come from gravitational waves, for example, from population properties or from internal properties of the neutron stars. Moreover, it is possible that the effect of the cosmological constant shows up once in multiband observations, where during the long evolution, you actually see the evolution becomes sensitive to the fact that a scale is introduced by the cosmological constant. This is almost all the things that I wanted to rush over during my last 2 or 3 minutes. Some of these things we can bring up again during the discussion session. I would like to end with this final slide and mention that also that there's been some recent interesting work on using gravitational wave standard sirens as calibrators for supernovae, and Satya is in the audience. We can also bring this up again for discussion. Thank you very much.
So if you have burning questions, please write them down, and we're going to use them in the discussion section, okay?